And our speaker today will be Niranjan. Niranjan is a PhD candidate from the 36th cycle, if I'm not wrong, and he's doing his PhD in collaboration with the University of Ghent under a joint PhD agreement. He's working on the characterization of the performance of self-healing concrete under extreme loading conditions. So with this, I just leave the floor to Niranjan. I will just share your presentation. Okay, so the floor is yours.
Thanks for your introduction. Good afternoon, everyone. I'm Niranjan. Today I'm going to talk about student autogenous self-filling of UHPC under repeated impact loading. So before I Okay. Sorry for this. I will briefly introduce about what is self-filling and why we are doing research on self-filling. What we're going to, what the purpose. So the self-filling is ability to concrete ability to heal by itself, by either autogenous or autonomously. So the main purpose is to reduce maintenance and repair works. In 2021 alone, there is a staggering amount of 40 billion USD was spent on identification, maintenance, and repair works, and it is expected to steadily grow at 7% per year in the future. So that's why it's important to introduce self-filling to reduce those maintenance and repair cost. Okay. So, what is autogenous healing? Autogenous healing, it can able to heal itself without any addition of engineered material, mainly due to the excessive amount of cementitious material like cement or slag, combined with low amount of water-mineral ratio, so which helps in heal its durability and mechanical properties. In autogenous sealing, there is a subsection called stimulated autogenous sealing, where any admixture or the additives we add in the concrete matrix, which helps to stimulate the self-filling, apart from its primary functions. In this case, if we have a crystalline admixture, we mainly add them to reduce the permeability. It also acts as a stimulating agent for self-filling. In case of the super absorbent polymer slab, we add them for long-term hydration to reduce the shrinkage. It also acts as a secondary function, it acts as a autogenous sealing. In autonomous sealing, we specifically engineered a few materials to enable the concrete to self-fill, such as bacteria, vascular network, micro-encapsulation, macro-encapsulation. These are like advanced and very costliest technique. Today I am going to mainly focus on the stimulated autogenous sealing based on the crystalline admixture. This experimental was carried out in Ghent University during my research stay in Ghent for 6 months. We developed a setup to carry out drop-in test. So it consists of the electromagnet located at 1 meter above the specimen and the 10 kg impactor which drops from there, and we have the plexi tube to guide them to center of the specimen, and we have a camera placed adjacent to the specimen to capture the rebound height. Apart from this, we have 2 load cells to measure the impact reaction force, and the laser and DAC kept underneath the specimen. The laser was pointing exactly at the center of the specimen along the projectile of impactor to measure deformation under loading. So I started with some preliminary analysis by taking 1 kg load dropped from the 1 meter height, and I measured the load cell values and the laser readings. What I conclude after like 50 drops, there isn't any difference between the first and the 50. Continues all 50 drops have this consistent same reaction force. The same goes for the laser reading. There is not much difference, so I concluded the 1 kg is not enough to evaluate the self-filling performance. Then I changed to 6 kg impactor. Then I started to notice there is a trend between the repeated impacts in dorsal reading and the laser deflections. But the issue is I am aiming for 50 to 150 micrometer crack width. Especially in UHPC, we have multiple crack width, which always, yeah, that's a good thing, and also it's a limited crack width in the healable range. But I couldn't able to reach this value upon several impacts. Then further, I changed to 10 kg. I have satisfactory the load cell and the laser reading trend, which both increases with increasing number of repeated loads, and I have some clear pattern. Still, it is not enough, but anyway, I can't further increase because I'm doing like manually. I have to lift and keep it there, so I can't lift another like 20 kg, and also our electromagnetic capacity, the maximum is like 10 kg. So if I increase more than like 15 kg, then it will probably be accidentally drop from the magnet. Then we calculated one specimen. Repeated impacts are noticed. Load cell reaction force versus number of impact. What trend we seeing here is after the first impact, we seen like consistent increase in reaction force. Then after a certain number of drop, we started to reduce. So this trend looks somewhere familiar. If you notice in the fluxual stress versus CMOD, we always, especially in UHPC material, we have a state hardening property followed by deflection softening. What I did is, if we in the first drop, we were anywhere in the stain hardening property, because in the first drop we have crack formed in the first drop itself. So if you draw the straight line, it meets somewhere the deflection, in softening region. So I consider that meeting point as a failure point. So that is the place where I have to stop the test. So this is mainly where I have to stop the test. Should I continue my test up to the complete perforation or complete destruction of the specimen? Does it need to go to complete perforation, or it is enough to stop before, and we can able to get self-healing performance with those impacts? So after some calculation, we decided these failure points work well. I can get the stiffness value from the laser readings, and also from remote height and other setup I have. It can able to give us a clear conclusion or a clear trend among repeated impacts. So we decided to place the failure point here where the lines meets the softening one, and continue a few more impacts after that. So you can see the video where we drop the 10 kg weight from 1 meter height, and it places exactly in the middle. And also there isn't any damage in the first impact. It is like a very robust material, and also the deflections are like very minimal, like around like 0.1 mm, not much. So we repeated several times. So especially not to understand what type of failure, I did like 100 times, more than 100 times, to understand what type of failure our specimen is face. In this case, I have the top portion is like perforation, and the bottom is the coning, so it's like a cone cracking failure pattern. And also you can see from the DAC image the cracks multiples with repeated impacts. This is for up to 6 number of impacts. Then like mostly after 6 number of impact, number of cracks stabilized. So there is no further increase, just so the cracks started to widen. So based on this preliminary analysis, I devised the experimental method. First, do some few tests up to failure, and find out what number of repeated impact requests to reach the failure point. Based on the failure point, take some percentage for pre-cracking. Pre-cracking in the sense, I do some number of repeated impact, then stop, then allow them to heal, then repeat the same test after a few months. The healing happens in 4 different environmental conditions: submerged, dry, NaCl, and 93% rate humidity. After this healing period, few set of specimen I repeat re-impact at 1 month and 2 months. This is especially to understand whether this healing can happen repeatedly, or the healing is like one-time phenomena or multiple time phenomena. To understand that, I did few specimens repeated impact in the interval of 1 and 2 months. Then all these specimens I impacted. There are few set of specimens I tested up to failure in the 7 months, and the remaining specimens I tested at the end of 4 months. So after this experimental plan concluded within 4 months. I did some non-destructive tests, especially the natural frequency analysis, to know the healing happens whether 3 days, 7 days, 14, okay, one shoe, how many days we need to properly heal the material. Especially this shows the increase in stiffness, so we did like 3, 7, 14, one shoe, 4 months. In case of a repeated impact, this number also follows after repeated impacts. Then we calculated energy absorption of the slab using high-speed camera, then the crack width using the microscope, then ductility of rate using the laser value. Then I used impact load cell. I didn't use them for quantify the cell building, rather I used this for an indication to stop the test. Then the DAC is the additional to verify our theory of the state ordinary property. For this test, we took 1.5-year-old specimen, which we assumed the long-term migration are already completed. Those specimens we got from the site CAS in Arizona. We got that to polymy. Each specimen has the dimension of 290 into 40 mm cube with the marginal error of plus or minus 5. The important thing to notice in the composition of the specimen is it has highly cementitious material, 600 kg per meter cube of cement and 500 kg of slab. Then steel fiber we have 120 kg per meter cube, that is 1.5% volumetric. Then we have the crystal amnesia which acts as a stimulating agent of 0.8% of cement. You can the contour. These are the like 6 slabs. We have the color denotes the fiber density. The fiber is not much difference. It's like 5% maximum. And we also have like a thickness variation, plus or minus 5. So because of that, we cut each slab into 4 pieces and allocate each piece to different healing environment. S is for submerged, WD is for wet and dry, RH for 95% RH. Then there are like few reference specimens we test after failure of the initial without any healing. So in this way, we get one specimen from all slabs, like 5 slabs for submerged, wet and dry 5 from each, then RH 5 slabs from each. So we distributed each slab for different healing environment, and also in the table also say the same. The S1 for the different. This is just a number. Each slab where we allocate a submerged one, WD is wet and dry from first slab, late humidity from the first slab, and the difference specimen from the first slab. So the number denotes the slab number, not the 1, 2, 3. Now to easily visualize the failure pattern, I take first drop as a reference material and change the ball graph. So you can see when the ball graph goes below, it's failure. In this case, first one we add here, I can say this is like some anomaly. So the first one and subsequent impact also shows reduction in reaction force. So the 39 number of drops is going to failure in this case. For VAC image, I will zoom it. So it will be easy. Okay. So in the first drop itself, we have multiple cracks. Then on the second drop, the number of cracks increases. Then on the third drop, the cracks started to branches from already existing cracks, where I can circle, you can compare. There is like small blue lines started to emerge from the from third impact. Then from fourth and fifth, the cracks are already stabilized, so there is no more new cracks. So the cracks are almost the same. So what changes happening is the cracks started widening. In the first impact, we have the maximum strain of 0.01. Then in impact 6, we have the maximum strain of 0.025. So the cracks started to widening after the third one. So this also shows our material is like strain ordering. If it like cracks started to open too much, we can't capture it in VAC. So we generally stopped most of the VAC work at the 6th impact. This is for all of the reference specimens, so I can clearly say all the specimens follow the same parameter. So at some repeated impact, it started to go down, so that is a failure point. Especially the slab 4, the failure point is 9, is mainly because the thickness variation and the 5% is a fiber content. So based on the fiber content, I made slab 4 and 6. The pre-cracking impact is not 3 times. Apart from other slabs, I considered the pre-cracking impact is 6 times. So it's I took 40% of the reference. Like a quantity. These are the healing environment I have for healing environment, and initiating environment I have the 5 slabs. The first 2 slabs I healed for 4 months, then 1 slab I healed for 2 months, then last 4 and 5 healed for 4 months, but I repeated impact on first 1 month. Second month is the same for all different healing group, except for the veterinary in NACL. I continued all the specimens for continuous 4 months. This bottom 2 tab, what we did is for veterinary, we considered 12 hours wait and 12 hours dry. We automated the process by using aquatic pumps, so every 2 hours the water will pump out. So we don't have to replace manually, and this the specimens we place in pouch, 90% pouch. Then after healing, we shake the blood still the failure point we defined at the beginning is still functions or breaks. So our surprise after healing, the pattern is similar. It still shows at the failure point after healing. So the black one is submerged, green is right, then the right is immediately chamber. So all specimens shows it clearly shows the failure point. So with this, we started to analyze other devices like the laser, high-speed camera, matching frequency. This one is deflection under impact. We measured using the laser. So the laser is placed exactly beneath the specimen at the middle around the impact projectile. You can see there's a clear trend. It increases with increasing deflection. So it's same for the reference 4. It increases with increasing deflection, except the reference 3. The concentration is mainly due to how the specimen fails. The specimen fails in a 3 different ways. It is in the next slide. This has happened. This specimen is snapped into 2 halves. This happens only in across specimens, so it didn't affect much of the results. So most of the specimens we experience is the cone cracking. So in the middle there's a cone. Then there is combined effect of the partial cracking from the edge and so we measure stiffness by doing moving average of 3 specimens. So sorry, moving average of 3 repeated impacts. So in this case, we measure how much the deflection changes after healing. Here is a 12% change in deflection, and how long it can be able to last. So the gain, healing, how long it will exhaust in repeated impacts. So in 6 impact, we lose whatever we gain in 6 months of healing. So that is what the impact resistance improvement after healing. So that is what also we aim for. We calculated similarly for all other specimens. Then yeah, so this is the overall chart. Some recrack, veterinary, NACL, recrack, then 90% average, some 90% margin recrack. So the maximum stiffness we observed is around 30%. Then it reaches up to 10% for veterinary. Especially the 90% orange really impacted one, we didn't see any improvement. So it clearly defines higher the water content, higher the improvement. So yeah. And also the gray bar denotes how many number of drops required to exhaust this 30% improvement. In this case, we need 50 number of drops to dissipate all this 30% improvement. So it varies for a different cleaning environments. Especially in continuously yield one, submersion veterinary is almost the same. Both requires 80 drops to dissipate the gain, while for 95% storage, half of the submersion value. This is for number of impact dissipates for the gain performance. Then for remote height, we captured all the impact, all the remote impact in a speed camera. Then we use the iMovie software to move each by frame. The frame to denotes, for example, this one is like the lowest when it, this is like a random. After impact, this is like second frame. Then frame 11 and 12 are the highest rebound. So that means it hit and it reached the maximum, but velocity is 0, then it once again fall back and rebounds. So when velocity is 0, we can clearly capture the maximum rebound height. The frame 11 and frame 12 are the same height. So because of the velocity 0, we can easily identify the maximum rebound. Then this frame 17 is starting to go down. So what I'm mentioning here is we use 120 frames per second camera. So 120 frames per second is like 4 times higher than normal camera. Normal camera uses 30 frames per second. So even with the 120 frames per second, it is easily captured. From the remote height, we calculate the residue coefficient. Residue coefficient is the square root of remote height versus the original height of problem. Here is 1 meter. Then we plotted against the situation of repeated impacts. The gray dotted line denotes at the beginning increase in time. So residue quotient means the elasticity of the material. In this case, at the beginning it's around like 0.3, so it's like 30% velocity. 1 means like upper velocity, 0 is so we have 30%, then it started to increase. This increase is due to not because the specimen is become more and more elastic under the load. It means because we have a large amount of fibers, we have multiple cracks, each crack is bonded by fibers. So at this place, the loads are carried by the fibers, not in the concrete fabrics. And also, I showed this in AC images. After the third impacts, the cracks started to open, but there is no new cracks. So the fibers acting like a spring. So that is the reason why we see increase in pattern. Not because the specimen is getting more and more elastic. Then after the healing, we see there is a reduction. So this reduction is due to after the impact, the energy started to absorb. So the reduction means it absorbs more energy. So we measured how much energy each absorb after the first drop after the healing. So we plotted for all the groups, almost all the specimen shows there is an increase in energy absorption after the healing, but we didn't really define any trend. All summer shaded orange, it shows everyone, but there is no trend. Then for natural frequency, it's one of the cost-effective tests. We only need like a microphone, and a microphone and a small hammer. The microphone are placed in the middle. Then we have like 13 points. On each point, I gently tap and record the acoustic reading. Then I convert the acoustic reading to frequency domain through Fourier series. From the frequency domain, I measure how much damage happening, how much the distance of this concentric circles like 3 centimeter from the center and some centimeter from the center. Apart from that, we have like multiple mode of frequency, so I did calculated another circle. Originally, I planned like third circle and fourth circle, so those two circles I have like multiple mode of frequency. So I eliminated them. Only those are like a single mode of frequency I use them to evaluate damage recovery calculation. So each specimens we have the damage up to like 20 to 45% maximum under the repeated impact. You can see from 2200 it's dropped to 2600. Then we measured the days on the end of 1 month. There is exponential drastic increase in viewing performance. Then we did repeated impact again at the end of the first month. Then again we put it in viewing condition. Then we did on the second month. Then again we measured it. So this period demonstrates our material can able to repeatedly lead upon multiple damages. Then this is like the overall performance. This is like continuous healing and repeated healing. So The natural frequencies mainly the performance depend upon the gravity of water content. The maximum is for submerged 92%, then followed by wet and dry from 80 to 87, Mediterranean NaCl, then orange 66%. For repeated heating conditions, you can see there is a residue left after the impact. Then it heals in another 1 month, then again it damaged, then it got. Then we did a crack closure for computation analysis. Submerged is completely healed, and it's just a image I will show after. For wet is like partial, for 90% it's like badly. And also the healing is happens mainly due to the division of unaided cement particle close to the crack. It started to move through the crack opening area. You can see there is like a few dotted on the outside of the crack. It's mainly due to the division of the unaided particles. We took like multiple images along the crack lip, then merged using the Photoshop and targeted the area in the Photoshop on subsequent months, then measured how much the crack lip is closed. For someone, and I divided the crack lip based on two categories, less than 50 micrometer and 50 to 150 micrometer, because a lot of literature points out that statement property material UHPC generally close 100% up to 50 micrometer, especially after the washing closure. Because of that, we divided the crack lip based on less than 50 and 50 to 150 micrometer. For 50 micrometer, the submerged one, I mean the 4 is completely closed, and also wet and dry is completely closed. With NaCl, it's not like above 90%, but orange is like 20%. For the larger crack lip, the submerged is closed at the end of 4 months. Then wet and dry is like 80%. Then the orange is like manually close to 20%. Then this is for like repeated impact criteria. For repeated impact, smaller crack lip is almost close 97% for the submerged. Then another 90% for wet and dry. But for orange, it's barely close. We couldn't able to keep up with the multiple damage because we don't have water availability. For larger crack, the overall crack closure got reduced for repeated impact, maximum closure is 60%, while orange is it didn't close after the second impact. It stayed as it is. So what we observe here is we usually see able to form multiple cracks, which enables the crack width within the given range. Then the stiffness of the material you go up to 30% for the submerged condition. From the natural frequency test, it can control, it can able to heal repeatedly, and it also depend upon water. The maximum for water, then wet and dry circulating water in NaCl, then orange. Then for crack closure, especially for smaller crack, submerged is like 100% closed, while for larger crack, submerged is 100%, wet and dry is 100 to 80%, while 90% orange is like 100% closed. That's it. Thank you for your attention.